Hi, welcome to another lesson at EDU Solutions Institute. Now, today on our IB Physics syllabus, we will continue on our part two of last week's lesson, where we looked at relativity, meaning the reference frames, which are also inertial reference frames. So in this week's, we're going to explore a little bit more and learn about our Maxwell's point of view in terms of relativity, as well as Lorentz factor, including in the equation. So stay tuned as we explore more on our HL topic of relativity. Let's go into it. Now, let's look at Maxwell's equation, Maxwell's view on the topic of relativity. Now, Maxwell was the scientist who actually put forward the link between magnetic field and electric field to create such a force. Now, what we have here is that when a moving charge is made to travel past a current carrying conductor, the moving charge will feel a force and will move at right angle to the particle direction and the magnetic field. Let us change the reference frame to see what really happens. Now, in this case, the observer is made to travel at the same velocity as the moving charge and the moving electrons. From this point of view, the charge that is moving is stationary to the current. Because if the current, electrons, and the external charge are moving at the same speed in the same direction, then relative to each other, they are not moving. So it also is stationary to the magnetic field as well. And in that case, according to that, there is no force because there is no relative motion between the charge and the magnetic field. So Maxwell presented a paper which established a connection between electrostatics, magnetism, and the speed of light. With four equations, he further linked these three quantities together. However, there was one stipulation in his equation that light travels at a constant speed as c, which is 3 times 10 to the 8 meters per second. Now, his equations clearly show that light is made of, and it is a wave particle can travel through space. A change in electric field induces a change in magnetic field, which in turn creates another change in electric field, which is how light propagates through an empty space. Now, if we consider this scenario in terms of we have a trolley or a train moving at 5 meters per second, and then a particle that's on it that's moving at 20 meters per second. And in this case, if we're stationary observer is looking at this event, then the velocity of the total framework would be the sum of their velocities because they're going in the same direction. And that's what's okay for Galileo's physics principle. Now, if we look at light traveling, and we have the train traveling at half the speed of light, then our stationary observer will they actually get or record the speed of this event as the sum of the speed of light and half the speed of light of the train. Maxwell showed that light can only travel at one speed, which is 1c, 3 times 10 to the 8. So therefore, what it does is to give us the second postulation of relativity, that the speed of light is a constant in a medium, no matter what the source of the light or the observer is doing. So what this means is whatever the observer observing the event or the source of the light doing, the speed of light will always be the same number, cannot be more than what 3 times 10 to the 8 is, and it will always be a constant within that event. So to account for the special changes that occurs when an object is in motion relative to another object, a conversion factor called the Lorentz factor is used. So therefore, because we know from our previous part 1 that if a certain event happens and we're in 2 different reference frames, we will experience or observe that event in different manner. And therefore, to account for this different manner, Lorentz actually has this factor that will help us to understand better what is happening. So what he uses the symbol of gamma, which is the Lorentz factor, which is 1 over the square root of 1 minus v squared over c squared. And v represents the speed of one inertial reference frame, and c represents the speed of light. So therefore, based on this graph, according to Galileo, if we plot this graph, we should get that the factor should always be 1. But according to Lorentz, the factor is not always going to be 1. So therefore, what we do know is to include that Lorentz factor inside our Galilean expressions, which gives us these equations from last week utilizing the Galilean factors. Right? So therefore, based on this, we see that space is no longer some absolute quantity that can be measured to some absolute length. Right? And also what this gives us as well is that it includes to us that we have the Lorentz transformation for time. Right? And these will be used in some examples right now. So here we have calculate the Lorentz factor of the following traveling objects. Given the speed of the object, and herefore all we do is to input it in our formulas, and we will get these different numbers. And as we can see, all these numbers are values greater than 1, right? Which shows us that all these objects are traveling to less than the speed of light. Now, the second question asks, what if the Lorentz factor, what happens to the Lorentz factor if the speed is extremely small than the speed of light? So if an object is traveling extremely slow than the speed of light, or the reference frame is traveling slower than the speed of light, then the Lorentz factor is equal to 1, and all observers will see the same thing. All will see the same thing. All are in the same reference frames. So what this tells us is if we find the Lorentz factor that gives us 1, then that means all the observers are within that same reference frame observing that event. And then next question is what happens if the speed is equal to the value of the speed of light? What does this imply for an object traveling at the speed of light? And then what that means is our Lorentz factor is undefined. Objects that have mass does not travel at the speed of light. Right? So therefore, nothing at this present moment we are able to quantify confidently that it travels at the speed of light. So hence, v will never be equal to the value of c, which is the speed of light. All right, third question here is an important question. It says we have some clocks in 2 reference frames or 2 frames of references, S prime and S. They are adjusted that when x is equal to x prime is equal to 0, t is equal to t prime, which is also equal to 0. And what this means is that they're starting from origin position at a time of 0 time. And then frame S prime at a speed of 0.90 relative to the S frame. And what that part means is that the S prime frame is traveling 0.9 of the speed of S frame. And then event 1 happens at when x1 is equal to 75 meters, y1 is 0, z1 is 0, and the time for t1 is 0.5 microseconds. And the event in terms of the second reference frame happened at x2 being 160 meters, y2 is 0, z2 is 0, and the time is 0.75 microseconds. So the questions are, in S prime reference frame, what's the distance between both events, x1 and x2, and what's the time interval, t1 and t2? So the first part is, what is our Lorentz factor? So we know that the speed of the two reference frames are 0.90 c relative to each other. So we input that value there, and we get a Lorentz factor of 2.294. So therefore, from our Lorentz factor, we know that a change in displacement in x is equal to the Lorentz factor minus the change in x2 minus x1 minus v t2 minus t1. So in this case, all we're doing is defining the reference frame changing in position. We input our Lorentz factor, we put what x2, x1 is, we put in what their speed is, and we put in what their time would be to give us a final value of 40.1 meters. So therefore, in reference to both reference frame, these events happen 40.1 meters in difference. But according to what was observed, compared to 85 that was measured in reference frame S. So in reference frame S, we just minus the 75 from the 160, which gives us 85. But from reference frame S prime, it is observed that there's a difference in 40.1 meters. And that's what this calculation tells us. Second part of the question is, what's the change in the time from the S prime? So again, we input our values in the change in time primes, and therefore, once we do that, we will get an inner time difference of 1.1 microseconds, which according to the S frame reference, we would get 25 microseconds, right? So therefore, there is a difference. So in our S prime reference frame, the event is happening in a shorter time period between events, but in S reference frame, it's happening in a longer reference frame time period, right? And that's what we see from our first part of the relativity to show us that based on your reference frame, you will see an event happening either longer or shorter. And that's what this equation tells us. Right? So, and that's the end of our part 2 of relativity, right? So next we will look at the final aspect, time dilation, length contraction in terms of relativity. So hope you understand a little bit more on relativity, and I'll see you next week as we explore more on our IB physics syllabus. Bye-bye.